So, moving forward, we've talked about insertions and different ways of adding things to a linked list. Let's now talk about removing things from a linked list a little bit. And what you're going to notice is, again, it's all of these things are very similar. Everything just basically comes down to manipulating the pointers of the linked list correctly so that everything gets reassembled in the proper manner and the list integrity is maintained. Okay, so again, in the Zybook and as well as the code I'm going to show you, we're basically going to be representing a remove after function. We're demonstrating a remove after function. So again, the Zybook code is almost a little bit more difficult to kind of follow than it really needs to be, but we'll work through it anyways. So in their Zybook code, they basically have a two-part if statement with a couple intermediary things in between. So the very first thing they're doing is they're saying list remove after 0, which in their code is a special case to remove the first element in the list. I don't necessarily agree that this is the correct way to do that. I feel like a remove after function should only ever remove something after the node you specify, and that you should have a different function or just a general remove function for removing the first node in the list. Or, for instance, if you wanted to remove a specific node, you would search for that node in the list, and then you would call a more generic remove function, which would then actually remove that from the list, regardless of whether it was the head of the list, the tail of the list, the middle of the list, etc. I feel that when you call a function remove after, that's the only thing it should do, and that it should not have any special cases like this built into it, because that just makes the function harder to use, harder to understand, and it's kind of non-standard behavior. Right, so the function I will show you when we write this up is only going to remove something after the node you specify. There's not going to be any special case for removing the first node in the list or the last node in the list, right? That's the job of a different function or a more specific or a more generic function's job than this one, right? But it still shows you basically the special things that are going to need to happen or the manner of handling the pointer manipulation in order to make sure everything's good to go. Right, so you can see in their code, they're basically saying that if cur node is 0, which is the node they want to remove, and list head is not empty, or the list is not empty, then what we're going to do is they go ahead and define this successor node, or the node that's going to follow the node that you want to remove. And you're basically saying successor node is equal to list head arrow next, right? So right now, if we're removing the head node, we need to know what follows it so that we just don't lose the entire list. So after we find our successor node, which is highlighted here, we can go ahead and we can say list head is going to equal that successor node, right? So we're going to redraw this pointer, move it around, and that is going to remove that node from the list. Now, of course, you also don't want to just manipulate the pointers and let that node kind of float off into space. You also actually want to call delete on that node to make sure it's freed from the system and those resources are given back. If you don't do that, you end up with what's known as a memory leak, where your program just starts using more and more memory the longer and longer it runs, which is not a good thing, especially if you have a long running process. So for instance, if you ever leave Firefox running for a very long time, you're going to notice that it just continually eats up more and more RAM the longer it runs. And that is because deep down in the core of Firefox, there is a long known, well known memory leak that happens, and which eventually leads to Firefox eating up gigs and gigs of memory. But that's a known problem that they have yet to fix, and I doubt they're going to fix. But anyways, so after we've kind of gone through our special case of removing the first node in the list, we can kind of go down and start looking at our more general cases of removing something from the list. So now they're saying they want to remove the node that directly follows the node 4. So basically we're going to end up removing the node 5 from the list. which if we look at what the pseudocode is going to be, we're going to fall down into our second if statement, our else if down here, and we're going to end up first, again, finding the successor node, and then basically jumping over the node we want to remove from the list. Right? When we're removing a node like this, we're often going to end up kind of jumping over it, and that will be the actual removal process. So if we want to take a look at that, we again will go ahead and try to find it. So we find our successor node, which is going to be this 2 over here. And then after we have found our successor node, we're going to see with this next line of code, cur node arrow next equals successor node, we're going to effectively jump over the 5 and hook this next pointer up to successor node, right? And what happens now is because we broke this link between these two nodes, right? The 4 node is the only thing that has a reference to the 5 node. So after we break that chain and kind of skip over it, nothing else on the system can actually ever reference 5 again, right? So that's the whole falling off into space, never to be seen again part. So it's important that before we actually make that jump, we either get another pointer to this 5 or we just delete the 5 before we make the jump and let it kind of fall off into space. So on the next line, we'll go ahead, we'll see this jump over 5, we break the reference, and then 5 just kind of goes away and floats off into space. And now this third case that they're going to show you is basically what happens if you are trying to remove the node after the end of the list, right? How does that work? Does anything happen? What could go wrong there? So in that case, we want to remove the node after 4 again, which is going to be this 2. So we go ahead, we find the successor node to the node we want to remove, which is null, right? Nothing's going to happen there. So if it's null, we would go ahead, we'll again do our whole little jumping over business, and we'll just effectively set that next pointer equal to null. But remember, our node hasn't quite disappeared yet because we still have the tail pointer pointing to the last node in the list, which is the node following the node we want to remove, right? 2 is the last node in the list, it's following 4, this is the one we want to get rid of. But we still have a reference to it, and it would be at this point we'd want to actually delete it from the system. After it's deleted from the system, this is the point where we want to check to see if we actually just removed the last node in the list, and if we did, then we need to reset where tail is pointing at which point we'd be good to go and the list is in its correct state. Okay, so that's kind of the high-level graphical overview of what removes look like. So now again, let's go back to our code and take a look at what this all actually looks like. Right, so we're going to define this this remove after function. And we're just going to pass it one thing this time, and it's the number of the node we want to find, just like how our insert after function behaved. So we'll come down here and we can define it. Void list remove after int num to find. And now the first thing, just like always, that we want to do is we want to first check to see if the list is empty, right? Because if the list is empty, we have nothing to remove and we don't want to do anything. All right, so we're going to check to see if head is equal to null pointer, right? If that was true, we could just return from this function. But what I prefer, just kind of make things a little more explicit, I guess, is we can check to see if head does not equal null pointer, then we're going to want to do some stuff. Otherwise, we can print a message that says cout list is empty, nothing to remove. Okay, so in the case that the list is not empty, now what we want to do is first start checking for our special cases, right? And a couple of our special cases may be if if the number we are trying to find is actually the last node in the list, right? Because if the number we're searching for is the last node in the list, then there's obviously nothing after it to delete, right? So one check we can do is if tail arrow val is equal to num to find, then we want to print out a message again. Nothing to remove. So we just alert the user. And then there's nothing else to do. Otherwise, after that, the next thing we need to do is basically check to see if the number we're trying to find, or if the node we're trying to find is actually in the list, which again, we've already done, right? Our insert after function has that taken care of for us already, right? So next thing we want to do is find the node, so we're just going to steal this code that we had before. I'm going to paste that in here. Right, so we make a walker node, we traverse the list, and again, the same thing we were doing before, we're checking, we're basically saying while there are nodes in the list to traverse, and while the value of the node we're currently on does not equal the one we want to find, just move on to the next node. And afterwards, if we either reach the end of the list or we find our node, this loop will quit, and we use the second if statement to say, okay, if we actually found a node, or found the node we're looking for, then we are going to actually want to remove it from the list, right? Which is actually going to be pretty straightforward. So the first thing I'm going to do is I'm basically going to say node star node to remove is going to equal w arrow next, and then after that we can actually do our whole little skip over the node that we saw before, right, with the green line. So to do that, all we need to do is basically say w arrow next is going to equal node to remove arrow next, right? So that's going to skip over the node to remove. So we have now attached w over, or we have skipped over the node to remove and attached it to the following node. And after we have done that, we now also need to check to see if the node we're removing is actually the tail of the list. So if tail is equal to node to remove, then we basically want to do similar to what the last two lines in the pseudocode were, and basically just say tail is equal to next, or I'm sorry, tail is equal to w, and then we can finally call delete and delete our node, right? And that's pretty much all there is to it. That's, put that there and that there. Sorry, one too many. And that is our basic removal function. And again, this removal function is just going to go and remove the node, or attempt to remove the node following a specific node in the list. This function will not be able to remove the first node or the head element of the list. In order to do that, you would need to basically make a copy of this function and write a much more general just remove function, which is an exercise you will need to do for the assignments in the class. All right, so at the bottom, what we can do now is we can now say L dot remove after, and because we had just inserted 235 into the list, we can say we want to remove the thing following 9, and we'll print out the list again, and hopefully this compiles. Who knows what I may have fat fingered. And we run it, and we can see here we first inserted 235 after 9. And then in the remove after function, we went ahead and deleted 235 from the list. And again, this should work for just about any number that we could find in here. All right, so that is basic removal. If you have questions, make sure to let me know. Otherwise, we'll see you in the next video.